Hello, this is recorded lecture on Chapter 3 from your Essentials of Radiographic Physics and Imaging book. This begins on page 26 of your book, and this chapter is about electromagnetic and particulate radiation. When we talk about electromagnetic and particulate radiation, as far as our role as a radiographer is concerned, the reason it's important for us to understand the different types of radiation is because realistically, it's our role to be familiar with all the different types of radiation to which patients can be exposed to, and it's our role to be an educator for those patients. Sometimes they ask us questions about radiation, or they might not understand something, and if at all possible, we should be able to answer their questions and help alleviate their concerns or their fears. We absolutely are a resource for the public, and we should be able to negate any myths or any misconceptions that people have about medical imaging. The biggest misconception they have is that what we do is harmful and dangerous, and x-rays are bad and they should not be exposed to radiation, which we know that what we do, what we give, is filtered radiation. So realistically, it's not something that you'd want to have done every day, but when done, ordered appropriately, and when imaging is done appropriately, it is not harmful or should be of concern to the patient. It should be something that we're able to make them feel comfortable about. So we should be familiar with the different types of radiation. We should also be able to answer any questions, understand how both ends of the electromagnetic spectrum are used in medical imaging. The bottom end of the electromagnetic spectrum, if you remember, begins with radio waves. And the reason that comes into play with diagnostic imaging is we use those along with a strong magnetic field in magnetic resonance imaging, and that helps create sectional planes or images of the body. The other end of the spectrum, we have X and gamma rays, and those are used, X-rays are used in diagnostic imaging, gamma rays are used in nuclear medicine, and realistically, the difference between the two ends is that one is able to ionize and the other one is not. So X and gamma rays have the ability to ionize matter, and if you remember so far our discussions of ionizing matter, by definition, ionization is either the gain or the loss of an electron from an otherwise stable atom. So when we radiate the patient, we do have the ability to ionize the atoms in the patient. So the potential is there to cause harm, which makes us understanding radiation physics and everything that takes place when we make that exposure all the more important. You should be able to be the patient's advocate in discussions of radiation with other health professionals, because remember, oftentimes you are the one with the most radiation knowledge in a room, even compared to physicians. Other than a radiologist, you probably have more knowledge than definitely the patient, and more often than not, any other medical personnel that is there. And lastly, you should be able to safely use radiation for medical imaging purposes, meaning you shouldn't just know how to push the button and take the image, but you absolutely should understand what is taking place when you push that button and make that exposure, from electricity coming out of the wall and supplying power to the control panel, the generator, the X-ray tube, exactly what happens in the X-ray tube to create the radiation, how the radiation exits the tube and enters the patient, specifically what happens within the patient when that exposure is taking place, and then how the radiation exits the patient and strikes the image receptor to actually create the image that the radiologist uses to diagnose. So that's kind of the goal of this introductory physics class, is to get you to understand. And when I say introductory, don't think that, what you learn in here is not valuable. It's absolutely the foundation of any further physics classes, which kind of take you a little bit deeper into how the X-ray machine functions and how things work, basically why and how things work. You don't have a good foundation in this subject matter, it makes everything else a little bit more challenging and more difficult. So I strongly encourage you to watch all the lectures, watch the PowerPoints that I've made, watch the videos that I've made to try and help you and show you some of the different concepts as best as I can, and make sure you do all the chapter outlines and homework questions, because that's only designed to help you. It truly doesn't do anything for me. I spent a long time studying this subject and understanding this subject while I was in school, as well as, you know, in order to teach it. So I absolutely encourage you to take advantage of everything that you possibly can. When we look at electromagnetic radiation, as far as its nature and the characteristics, pretty much electromagnetic radiation is an electric and magnetic disturbance that travels through space at the speed of light. All right, and that's important when we talk about the velocity or the speed at which all electromagnetic energies travel. It's at the speed of light. So it travels in wave form. When we look at some of the characteristics of electromagnetic radiation, what we end up with is an electromagnetic spectrum, which is a way to order or group all the different electromagnetic radiations. And as far as the members of the electromagnetic spectrum, which we're working towards looking at the picture on page 27, that figure 3.2, that electromagnetic spectrum has all the electromagnetic energies listed on there, starting from the low end of the spectrum with radio waves and working our way up to X and gamma rays. So on that spectrum, all of those particular things, radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays, all travel at the same velocity. They travel at the speed of light, which is 3 × 10⁸ meters per second. The only thing they vary in is their energy, their wavelength, and their frequency. Okay, so they vary in their energy, their wavelength, and their frequency, but they never vary in velocity because they all travel at the same speed. Now, this is the actual electromagnetic spectrum. And notice how, again, it starts with the low end of the spectrum at radio waves, and then notice how when we look at the waveform, we end up talking in this chapter about wavelength, which is the distance between 2 successive points on a wave, either peak to peak or valley to valley. Notice as you move from left to right, the wavelength gets shorter. Okay, and the frequency, which is the number of times the wave passes in a given time frame, notice how the frequency increases, as does the energy. Okay, so when you move from left to right, the energy increases. So radio waves tend to be fairly weak, microwaves may be a little bit stronger, infrared light, and then you have visible light, ultraviolet light, and then X and gamma rays at the top end of the spectrum, meaning they have the shortest wavelength, the highest frequency, and the most energy of anything on there. But they all do travel at the speed of light. Electromagnetic radiation is a form of energy that actually originates from the atom. So electromagnetic energy gets emitted when changes in the atoms occur, like when the electrons undergo an orbital transition, meaning they switch shell levels, or the nucleus of the atom emits excess energy in order to regain stability. Electromagnetic radiation can exist apart from matter, and it can travel through a vacuum. Okay. Unlike like ultrasound, requires matter. You have to place that transducer on something so that those sound waves can bounce off to give you an image. Whereas with X-rays, which are on the electromagnetic spectrum, that is not the case. They do not have to have matter in order to be created and be effective. Now, would we have an image? No, you do need something to pass through in order to create the image, but they can exist apart from matter, meaning you can still have radiation. Even though you don't have matter, you can create radiation. But in order to make an image, you do have something to pass through. And X-rays are not only created in a vacuum, but they actually travel through a vacuum, unlike other forms of energy. When we look at electromagnetic radiation, it actually exhibits properties of both a wave and a particle. And it depends on its energy, and in some cases its actual environment. And this is called the wave-particle duality theory. And essentially what that says is there's two correct ways to describe electromagnetic radiation. Okay, if we talk about it based on its wave characteristics, then we tend to talk about the wavelength, the velocity, the amplitude, and the frequency. Okay, now what do I mean? The wavelength is typically the distance between two successive or equal points on a wave. So either peak to peak, or you could measure valley to valley. That represents the wavelength. The frequency is the number of times the wave passes in a given time frame. So they're telling you, if they're showing you this time frame, the wave passes 3 times in that time frame. So the frequency right here is 3. The amplitude is actually the maximum height of a wave, and it tends to define its intensity. And velocity, we said, is always constant, the speed of light. So if we speak of electromagnetic radiation with regard to the wavelength, the frequency, the amplitude, and the velocity, you tend to be talking about it in wave form. Okay, so waveform is how we talk about it, but typically with X-rays, we tend to talk about those more in particulate form, and we'll talk about that in a few minutes. When we talk about wavelength, again, it's the relationship between, or I'm sorry, wavelength is the distance between two successive points on a wave, and the relationship between wavelength and frequency is inverse, meaning when you look at this wavelength, okay, the wavelength is relatively long compared to, maybe I should look at the spectrum, it'd be a little bit easier to show you. So wavelength and frequency are inverse related. So here we have a long wavelength, right? And the frequency is very low. So a long wavelength, low frequency. But when you get over here, the wavelength becomes shorter. So the wavelength goes down, but the frequency actually increases, meaning the shorter the distance between these, more frequency occurs. The greater the distance, when the wavelength increases, the frequency is decreased. So they actually have an inverse relationship. All right, so wavelength decreases, frequency increases, and when the wavelength increases, frequency decreases. So they're inversely related. Typically, we talk about wavelength, it's expressed in meters. Frequency, which is the number of times the wave passes in a given time frame, which is typically 1 second, and that is expressed in hertz. And usually 1 hertz is equal to, a hertz is typically equal to 1 cycle per second. Hold on 1 second, let me make sure I'm not telling you wrong on that. I'm pretty sure I'm right with that the hertz is 1 cycle per second. But frequency is measured in hertz. Yes, 1 hertz is defined as 1 cycle per second, and that's on page 28. So frequency is expressed in hertz, wavelength is expressed in meters. when we look at the formula, there actually is a mathematical formula to calculate wavelength or frequency, and that formula is velocity equals frequency times wavelength. And these are the Greek representations of frequency and wavelength. All right, so when we look at that, frequency times wavelength gives you raw velocity. But when we talk about electromagnetic radiation, remember that our velocity is constant, so it changes to the constant is equivalent to the frequency times the wavelength. So when we say the constant, it's the speed of light. All electromagnetic energy travels at the speed of light, which is 3 times 10 to the 8th meters per second, or 186,400 miles per second. Either one of those is acceptable, whether you're talking about the British system or the SI system. But the velocity of all electromagnetic energies, whether you're talking about radio waves, microwaves, X-rays, gamma rays, any of those on that spectrum, all have a constant velocity. So when you change the formula and you're speaking about electromagnetic radiation, you could calculate the frequency or the wavelength because this number is always going to be a constant. So if you were solving for frequency, you simply move that on the other side of the equation. So frequency would equal the speed of light divided by the wavelength. And if you were trying to solve for the wavelength is equivalent to the speed of light divided by the frequency. So you could solve for either of those factors when you're dealing with electromagnetic radiation. If you were dealing with some other form that wasn't electromagnetic energy, then it would simply be the velocity is equivalent to the frequency times the wavelength. And all of that information is actually found on page 28. All right. When we look at some other nature and characteristics of electromagnetic radiation, it can be characterized by how it actually interacts with matter. Okay, so when we talk about electromagnetic radiation interacting with matter, it tends to exhibit more characteristics of a particle, and that's dependent on its energy. So when you have an individual particle or a photon of energy, okay, so the smallest unit of electromagnetic energy is considered a photon, right? So one photon, when we talk about X-rays, we tend to speak of them like the primary beam is made up of photons of electromagnetic energy, and each photon has an individual energy value. And when those interact with matter, meaning our patient, they tend to behave more like particles versus waves. All right, so the higher energy photons like X-rays and gamma rays act more like a particle, and a low energy radiation like the radio waves and the microwaves on the low end of the spectrum act more like waves, because you tend to speak about radio waves. Think about AM FM stations. You tend to talk about what frequency they broadcast at. You tend to talk about the wavelength. How far away is the tower that's sending out the signal? But when we talk about X-rays, we tend to talk about them more with regard to their energy value. So X-rays behave more like particles. The low end of the spectrum tends to behave more like a wave, where you talk about the wavelength, the frequency, the amplitude, things like that. They also reference that the intensity, and remember, anytime we think of intensity or hear intensity, you want to think quantity or number. But the intensity of electromagnetic radiation diminishes over distance. Now, what does that mean? That means that the farther away you are from the source, the less radiation you receive. It also, you can think about it in terms of light, because X-rays behave a lot like light, and this is called the inverse square law. Okay, so when you think about a light, or if you were sitting by a campfire, the further away you are from the light or the farther you are from the campfire, you're not going to be able to see as well, because when you increase your distance, the light, the source of light, is farther away, which means you're not able to see as well, correct? Like if you're trying to read something and you're right up next to the lamp, you're going to be able to read pretty well. But if you go 12 feet away from that light source, you're probably not going to be able to read it as well as when you were right up next to it. So the same thing happens with radiation. When you're farther away from the source, you tend to get less radiation. But the closer you are to the source, you get more radiation. So when we talk about the fact that distance is one of the greatest things that a technologist can use to protect themselves from radiation, we always say that if you can even take one step back or one step behind the radiologist or move one step away, you're going to get less radiation exposure than if you stay close to the source. And remember, the source is your focal spot in the tube. I know we haven't really talked about that much, but that's where your radiation is coming from, is from the focal spot in the tube. That's where your radiation source is. So the farther you can get from that, the lower your radiation exposure will be. And again, this is called the inverse square law. And mathematically, if you look on page 29, the formula is I1 over I2 is equivalent to D2 squared over D1 squared. And I will do a separate video and show you mathematically how to solve for that and what it actually looks like. But for now, we'll just look on page 29 and reference that as the inverse square law, which says that the intensity of radiation diminishes or decreases with an increase in distance. When we look at X and gamma rays, they absolutely have the characteristics of both waves and particles, but because they have higher energy, they tend to exhibit more particulate characteristics than those at the other end of the spectrum, the low end of the spectrum, like the radio waves and microwaves. All right. Now, when we say they exhibit more particulate characteristics, they do have the ability to burn the skin. Their intensity does vary according to the inverse square law that we just mentioned, and they do have the ability to ionize matter. Okay, so the thing about particulate radiation, especially with regard to X and gamma rays, is that they have the ability to ionize matter, meaning if those photons that are in the primary beam have enough energy, they can actually remove electrons from the orbit of the atoms when they interact. So this could take place in the body. Anytime there's gain or loss of an electron from a stable atom, it is called ionization. And remember that when you ionize the atom, you create an ion, whether it's an anion or a cation. All right, so the fact that we're able to do that with the X-rays is what makes them dangerous if we're not properly exposing the patient, we're not following all the things that we will learn to guide us to follow the Alara principle. So when you ionize tissue atoms, for example, you do have the ability to alter the DNA and cause changes in the cell. And remember, if enough changes are there and the cell is in a mitotic state or reproducing state, then you do have the ability, in theory, to create cancer. What's the difference between an X and a gamma ray? Basically, X and gamma rays come from different sources. Their point of origin is different. Gamma rays come from the nucleus of a radioactive atom, and it represents the excess energy that that atom is trying to give off in order to reach a stable state. We tend to see use of gamma radiation in nuclear medicine and radiation therapy. X-rays, on the other hand, originate through an interaction between electrons and atoms in the X-ray tube. So we actually create X-rays in the X-ray tube between the electrons and the atoms, the tungsten atoms on our target. And gamma radiation comes from the nucleus. X-rays come from the orbital shells. So again, I'll show you that in the other video. So if you could see an X-ray and if you could see a gamma ray, you absolutely would not know the difference between the two unless you saw where they came from. If you could visualize where it came from, then you would know which one was a gamma and which one was an X-ray. But as far as any other distinguishing factor, there really isn't any. As far as the rest of the spectrum, if we go back to the low end, the radio waves are at the lowest end of the spectrum. The reason we usually reference them is because we do use them along with a strong magnet in magnetic resonancing. And they do not have the ability to ionize. Honestly, nothing on the spectrum can ionize other than X-rays and gamma rays. Microwaves are the next one. A lot of times we think of microwaves, they transmit cell phone signals, they heat food, and again, microwaves absolutely do not have the ability to ionize atoms. They can heat tissue, but they don't ionize atoms. Infrared light, sometimes when we think of infrared light, you use it to send information between electronic devices like the remote on the TV. The signal is sent. Sometimes you see a red beam, or you have to aim the remote just right at the TV to get it turned on, and that is using infrared light. Infrared light does not and cannot ionize atoms. Visible light represents the colors that we see all around us. Okay, so it's likely the most familiar member of the electromagnetic spectrum because it's all the colors visible to the human eye. It's just a small portion of the electromagnetic spectrum, and again, it does not have the ability to ionize atoms. Ultraviolet light has energies approaching that of X and gamma rays, and as far as ultraviolet light, typically those are used in tanning beds. The reason that this is dangerous, again, they're not ionizing the atoms, but what it does is ultraviolet light is the part of the sunlight that actually causes darkening of the skin or burning if you have excessive exposure. And what the ultraviolet light does is it stimulates melanin production in the skin, causing that darkening or damage to the melanocytes that can result in cancer, but it doesn't ionize atoms. So I'm not saying that ultraviolet light is safe because it actually stimulates the melanocytes, and then if they're overstimulated, you can actually cause cancer. So if you've ever read the disclaimer, if you were to use a tanning bed, if you ever read the entire disclaimer, you probably wouldn't want to get in the tanning bed because it's kind of scary when they talk about all the things that can happen. So they can be harmful, but they do not ionize atoms. And that's everything besides X and gamma. So just to kind of sum it all up, radio waves are used for radio stations other than like satellite signals. Used in MRI, can they ionize? No. Microwaves, cell phone signals, microwave ovens, but no ionization. Infrared light is communication between electronic devices, but no ionization of matter. Visible light allows us to see and perceive color, but no ability to ionize matter. Ultraviolet light, typically used when we think of it as far as a source. Tanning beds are a source, but they do not ionize, but they are not necessarily safe either. X-rays used in medical imaging, diagnostic imaging, radiation therapy. Yes, they absolutely have the ability to ionize matter. In gamma rays, nuclear medicine, and again, radiation therapy, they do have the ability to ionize matter, and they are harmful to patients. So both of these have to be used. There has to be a great deal of knowledge behind technologists, radiation therapists, in order to use these effectively to treat patients. When we look at particulate radiation, this is over on page 30 and 31. Particulate radiation, we have two sources of that. We have alpha particles and beta particles, and these do have the ability to ionize matter. They have enough energy to ionize matter, and typically with particulate radiation, we see this more used in nuclear medicine or radiation therapy, but not in diagnostic radiology. When we look at particulate radiation, we usually are speaking of radioactivity, and that is generally a term that's used to describe the process where an atom that has excess energy in its nucleus will emit particles and energy trying to regain stability. If you think about it, does anybody like to be unstable? I can't think of anybody that would say, oh, I love being unstable. Atoms are the same way. They don't like to have excess energy. They like to have the right amount that they're supposed to have, nothing more, nothing less. So when they have excess energy, they try to get rid of that excess energy, and that is called radioactivity because they're trying to get back to their normal state. And when they do that by emitting nuclear particles or emitting energy from the nucleus, that is called radioactive decay. Any elements that are made up of atoms that have an unstable nucleus are said to be radioactive atoms. And again, we use those in nuclear medicine as our radioactive tracers that we give to the patient. And they can also be a source that are used in radiation therapy. As far as particulate radiation, it says that a substance will not radioactively decay all at once. It could literally be minutes up to billions of years. And that the amount of time it takes for half of the remaining atoms in an amount of the element to decay is called its half-life. Okay, so when you have radioactive decay, it doesn't happen all at once. It can be minutes or billions of years, and the term that describes the rate at which it decays is called its half-life. So some half-lives, like if you think about radium-226, the half-life is 1,620 years. So at that point in time, half of the unstable atoms would be left, and half of it would be left another 1,620 years, and so on. So typically the half-lives measure radioactivity because that's how they decay. Now, typically the things that we use, like radioactive tracers, their half-life is in a matter of minutes, not 1,620 years. So the two particles that we tend to look at are alpha particles and our beta particles. So when we look at an alpha particle, typically it's two protons bound to two neutrons. So it has the same makeup right here as a helium atom. Two protons, two neutrons. It looks exactly like a helium atom. So this would have an overall net positive charge. Alpha particles tend to be very big and very heavy, and they're not able to travel very far because they're so large and they can't penetrate most objects. Typically, if you had an alpha particle passing through the air, you could put up a piece of paper and stop the alpha particle. All right, so they're kind of big and oafy and they can't go very far, but they resemble a helium nucleus in their makeup. Okay, so that's an alpha particle. A beta particle is simply an electron that comes from an unstable nucleus. So this electron is emitted from the nucleus of an unstable atom. So it spits out this, really it's an electron, but because it's coming from the nucleus, it's not like these electrons. It's typically called a beta particle. So it's not an orbital electron. It's actually coming from the nucleus, and that's a beta particle. They tend to be much smaller than an alpha particle. they're much lighter than an alpha particle, and they can penetrate things much easier than an alpha particle. So they can travel farther, and they can ionize a lot of atoms along their way. So they don't originate in an electron shell. It comes from the nucleus. They're lighter, smaller, and travel farther, and they can ionize many atoms along their path. When we look at particulate radiation, specifically the beta particles can have a positive or a negative charge. So remember, the beta particle is the electron coming from the nucleus. So right here, this one has a negative charge, and a negatively charged beta particle coming from the nucleus is called a negatron. Okay, I have it in here a little bit further, but the negatively charged beta particle is different from an electron because it didn't originate on the orbital shell. It originated in the nucleus of the atom. Okay, so the negatively charged beta particle is called a negatron, and the positively charged beta particle is called a positron. So if this electron that got released from this unstable nucleus came out and it had a positive charge, if this came out and had a positive charge, that would be called a positron. Now, where have you heard that before? Well, in PET scanning, we have positron emission tomography, because when you put these tracers in the patient, the radioactive tracers, what happens is, in order to give off the excess energy when it's undergoing radioactive decay, it emits positively charged electrons from the nucleus that are called positrons. When those are emitted and released from the tracer, you actually use a gamma camera in nuclear medicine to detect that. So that's how PET scanning actually works. So a positively charged beta particle is called a positron. And they talk about when a beta particle gets stopped by a collision with other atoms, like when it runs into another atom, it simply joins the orbital shells of those atoms just like an electron. So when they're emitted, it's a positron or a negatron, but once they interact with something or bump into something along the way, they simply would fill a void on the orbital shells and become just like an electron. All right. When we look at this last part of the chapter, we have to look at and understand how ionizing radiation exposure happens. And typically when lay people tend to think about radiation exposure, they typically think of a nuclear event or, dental x-rays or medical x-rays. But realistically, we get exposed to ionizing radiation every single day in our daily lives. And typically that is either as natural or background radiation. Whereas when you're talking about medical radiation, like an x-ray from the dentist, or when you go to get an x-ray of your hand or your chest, that is man-made radiation. But natural and background radiation occur as well. We have cosmic radiation, terrestrial radiation that comes from the ground, internal radiation, and medical radiation. So when we talk about natural or background, it can come from cosmic sources, terrestrial sources like radioactive decay of minerals that are occurring in the earth. You have internal radiation where you ingest foods and minerals that have traces of radioactivity because they were grown in the ground. And then you also have medical sources like our x-rays, whether it's a dentist or medical x-rays, nuclear medicine studies. When you think about the total dose that patients get from these sources, it all varies according to their geographic location. Okay, so we get exposed to ionizing radiation in little doses every single day. So some amount of exposure is okay. The medical radiation that we're exposed to typically is filtered, so it's not as dangerous as going outside in the sun with no sunblock. flying in an airplane where you're closer to the sun and there's no shielding on an airplane. Okay, so we have to be able to explain these kind of things to lay people so that they understand that what we do, yes, it can be dangerous, but it doesn't mean it is dangerous just based on the fact that we're utilizing ionizing radiation, because what we use is filtered radiation, whereas some of these things, the natural and background radiation, cosmic, terrestrial, they're not filtered. There's nothing you can do about it. You just are exposed to it daily. So not only are we exposed to it in our job, but we do get exposed to it in our everyday lives as well. So it's on us to be that educator for the public and to be able to explain these things to the public to help dispel any fears or myths that they might have. All right, and that takes us to the end of chapter 3, where we talk about electromagnetic and particulate radiation. If you have any questions or comments or concerns, I do hope you write down. Make sure you look at the accompanying video where we will go in depth and visualize some of these things, especially the inverse square law, a little bit more. And if you have those questions, make sure you write them down, and I will help to clear up any confusion when we meet again. Thank you so much.